All right, so we're going to look at Unit 13 next, and that has to do with probability. And in general, you know that probability means how many ways can something happen out of the total number of ways that are possible. So to be able to get to this point, we need to know how to find out how many ways are possible. And some of that is just some basic counting. So we're going to look at some basic counting methods first. All right, probability will come at the end of this unit. It's a very short unit. So first we're going to look at sets and set notations. So if we have two sets of numbers, A and B, are equal, that means they have exactly the same elements. So a little bit of notation here is if I have a set A, usually we write braces around whatever is inside A, and what is inside A is called an element. Okay, so the braces is set notation, and the list of things that are inside the set are called elements. So if set A and set B have exactly the same elements, like I've written here, then A would be equal to B. The sets are equal. If each element of set A is also an element of set B, we say that A is a subset of B. And this is how we note something being a subset. Well, up here, we have the exact same elements in A and B, but we could have a set A that has 1, 2, and 3 inside as elements of set A. And if I have in set B, I could have 0, 1, 2, 3, 4, 5 are the elements of set B. So if we look at this, each element of set A, 1, 2, and 3, can be found in set B. Okay, so A is a subset of B. If A is a subset of B and they're not the same sets, which means they don't have exactly the same elements, this is called a proper subset. Okay, just a little terminology here. And we say A is a subset of B. And that basically means that there are some elements over here that are not in this one. So the sets are not equal. There's also a set that has nothing in it. If I were to write like this, this is an empty set, and we can also notate it like this, or like this. All right, so there are sometimes sets that don't have anything in them. So one thing to note is that the null set, that's what this is called, the null set is a subset of every set. All right, so here in example 1, it says to write down all the subsets of this set. All right, so first we're going to write down the null set, and then we have a set with just A in it, a set with just B, a set with just C. Then we might put two of the elements together. We might have A and B, we might have A and C, and we might have B and C. And we might have the set with all three elements in it. A, B, and C. So if I were to count how many subsets there are, 1, 2, 3, 4, 5, 6, 7, 8. So here I have 8 subsets. And there's actually a formula that we can use, and that has the number of elements. We need to count the number of elements in the set, and the number of subsets is 2 to the n subsets. So in this case, we have 3 elements in the set, 1, 2, 3. So 2 to the third power is 8. Excuse me. A tickle in my throat. So in example 2, it says that in a survey, 100 college students, we have 35 registered in college algebra, 52 were registered in computer science, and 18 were registered in both courses. So how many students were registered in college algebra or computer science? So a lot of times you're going to see this information in the form of a Venn diagram. So we can do that here by making a rectangle, and we have circles that are going to represent the courses. So let's say that this is college algebra, and we know that in college algebra there were 35 registered, and then this would be computer science. And we know that in computer science we have 52 registered. And we know that 18 people were registered in both courses. So in between here, we have 18 people. So if I'm making a Venn diagram, the overlap is where the student takes both courses. So if there's a 35 total in college algebra, there are 17 students that just take college algebra, because 17 students only in college algebra, and then the 18 students that have algebra and computer science. And then this circle represents the number of students in computer science, which is 52, but 18 of them are also in college algebra. So we have 34 students that are registered in just computer science. Okay, and this 18 goes to both sets. All right, so part A says how many students were registered in college algebra or computer science. Now, we're going to be working with some important words, and or. And means that it has to be in both sets, or means it can be in either set. And we use some notation here. If we have an or, this is the union of two sets. It can be in one set or it can be in the other set, but we count all of them, this or this. And is an intersection, and the intersection means that a student is in both sets. So the intersection is right here. Now, if I'm counting how many students were in college algebra or computer science, I can add the students that were just in college algebra, the students that were just in computer science, and then I can count the overlap, the number that are in both. So how I can write this mathematically for part A is that I can take the number of students that were in college algebra and have a union with the number of students that were in computer science, just computer science, and have a union with the number of students that were in both. And I'm just going to write it in this notation for right now, because technically and I'll just show this down here, we could say that both would be computer science intersection college algebra. So this would be CA intersection CS. All right, so if I have the number of students in just college algebra, that's 17. And that means I'm going to add the number of students that are in computer science, 34, plus the number of students that are in both, which is 18, and that gives me 69. Or another way to do this is to take, if I say that college algebra is set A and computer science is set B, I could take the set A union set B, that means I'm going to add them all together, and subtract the intersection of A and B. So A intersect B. So if I look at this, I see here 35 people take college algebra, plus 52 people take computer science, and then I'm going to subtract the number of students that overlap, which is 18. And then if I add these together, I'm going to get 69, which is what I had before. In part B, it asks how many were registered in neither course. Well, in the directions, it said that we had 100 college students. Okay, so this is showing us we have 69 registered in either or both computer science or college algebra. So in part B, I just need to take that number away from the total, and I get 31 students. And I would show that in my Venn diagram as just 31 students that don't belong to either course. All right, so on the next page, it says if A and B are finite sets, that means there's a definite number of elements in each set. That if I have the union of two sets, I'm going to add the number in each set and subtract the number that overlap. So this is the overlap, the ones that belong to both sets. Okay, and this is a union of two sets. If A intersection B is the null set, that means they have nothing in common. All right, so if there's nothing in common, this would what it would look like on a Venn diagram, where they don't overlap. All right, so a little review there on sets, set notation, and Venn diagrams. In example 3, it says in the year 2004, U.S. universities awarded 42,155 doctoral degrees. In this table, it lists the number of doctorates conferred by the board of each of the fields of study. All right, so if we look in here, each of these different fields of study are independent of the other. So if you're getting a doctoral degree in 2004 in physical science, that's a different set of somebody that's going to get one in social science or education. So these are independent of each other. I'm going to zoom back out here. That means somebody is not going to be awarded a degree in engineering and life sciences at the same time. Okay, so there's not going to be any overlap. If I were to do a Venn diagram, these circles are just going to be out there separately. Okay, kind of like this. No overlap there. So in part A, it's asking how many doctorates were awarded by the universities in physical science. So physical science is here and life science is here. So we have the number, this is part A, the number of physical science, or means a union, that means I'm going to add them up, or life science. So since there's no overlapping, I'm just going to add them together. So physical science was 6,049 and life science was 8,819. Add them together and I'm going to get 14,868. In part B, I want to know how many doctorates were awarded by the universities in physical science, life science, or engineering. So I could take this number and then add in the engineering number. So I have physical science, and I'm going to union that with life science and union that with engineering. So since I already know these two, I'm just going to add engineering to that. Where's engineering? Right here, 5776. Add that together, and I get 20,644 degrees. Now, these are all independent of each other. And here's another example of things that are kind of independent of each other. And you've seen examples like this used a lot throughout your years of math. But here we have a fixed price dinner at Aqua provides the following choices. So you're going to choose an appetizer, which is either super salad, an entree, which is baked chicken, broiled beef patty, also known as a hamburger, baby beef liver or roast beef au jus, and then you're going to choose a dessert from ice cream or cheesecake. And they want to know how many different meals could be ordered. All right, so we're looking at all the different ways that I could match up a soup, or I'm sorry, an appetizer, an entree, and a dessert. And here, you're going to be making three choices. So here, you first choose an appetizer, and here is your entree, and here is your dessert. Now we need to count up how many items are available in each category. So for an appetizer, you can choose a soup or salad, so that's 2. So we're counting the number of entrees, 1, 2, 3, 4. And then counting the number of desserts, ice cream or cheesecake, that's 2. Now, again, you've been doing this probably since middle school, and there's a property that allows us to just multiply these together It's called the fundamental counting principle. All right, so how many choices can be made at each station, and then we multiply them together. So I have 8 times 2 is 16 different combinations, or 16 different meals can be made by selecting the different things at each station. In example 5, it says how many 2-symbol code words can be formed if the first symbol is an uppercase letter and the second symbol is a digit. All right, so here we're making two choices. All right, so the first part of our code word, there's 2 elements. The first part is going to be a letter, and the second part is going to be a digit. Okay, so there are 26 letters to choose from and 10 digits to choose from. Multiply them together, and we have 260. In example 6, we have 4-digit passcodes, like if you are putting a passcode on your phone. Okay, you have 4 digits, and each one of these represents an element in each of the digits. So in the first space, we can have 10 different numbers to choose from. In the second space, we can have 10. In each of these spaces, we can have 10 different numbers. And that's because we can repeat. Okay, I know on mine I have numbers that are the same. Okay, it could be like 2243, where the 2's repeat, or 7117, and in that case the 7's and the 1's repeat. But in any case, the possibilities of different numbers, different passcodes, is going to be 10 to the 4th power, or a 1 with 4 zeros, which is 10,000. Okay, so if we think about it, that's not a whole lot of different trials if you were looking at random to do that. So at some point somebody says, oh, that's not safe enough, so maybe we should do this and have a 6-digit passcode. And in that case, we would have 10 digits to choose from in each of the in each spot, in each of the 6 different numbers, and that would be 1,000,000 different numbers, or 1,000,000 different 6-digit numbers. Okay, which I think companies are now saying that's a little bit more secure. But if you think about it in your passwords for computers and stuff, you have to have a digit somewhere in your password, and it can be any random numbers, letters, symbols, have to have a capital somewhere. So when you're looking at passwords on your computer, you have a very, very secure passwords, because it doesn't even tell you how many spaces you have to fill up. Okay, so this is more secure, but your passwords on your computers are way more secure. All right, so there's a problem set on this, just on counting, and we'll be back next time for more ways of counting.